after 11. Um, so let's get started. The two topics today are thermal shock and corrosion, and that'll finish up the properties, which are the background for the different types of refractories, which we'll discuss basically for the rest of this course. So thermomechanical properties is basically thermal shock, and there's four topics here: thermal stresses, thermoelastic theory, thermal shock damage resistance theory, and how the structure affects the thermal shock behavior. So thermoelastic theory and thermal shock damage resistance theory are two different ways of designing a material to resist thermal shock. In the thermoelastic theory, you design a material to resist any type of failure, any type of thermal shock damage. In the thermal shock damage resistance theory, you allow damage to take place in a controlled manner so that you have a very gradual type of failure. In the thermoelastic theory, you're basically designing a high performance ceramic, such as a turbine blade, where you don't want any type of failure, any type of catastrophic failure. And the other approach for thermal shock damage resistance, that's how you design a refractory. You start out with a weaker material, you allow it to accumulate damage, but it doesn't fail completely. So we'll go over those different approaches. So for thermal stresses, they arise from temperature gradients. Refractories can be subjected to a rapid quenching. They can be subjected to a more gradual type of quenching. So rapid quenching would be the most severe type of thermal gradient with the most severe type of damage. So quenching is takes place during cooling. You can also have rapid heating, but what happens during cooling is the outer surface of the refractory is basically contracting while the inner surface is not. So you develop tensile stresses on the surface. Heating, the opposite happens. The surface is expanding faster than the interior, so you develop compressive stresses. So ceramics, refractories, whatever way you look at them, the tensile strength is always much lower than the compressive strength. So thermal shock is always much more severe in cooling than heating. So the cooling cycles are what really does the damage to a refractory. So for the rapid quenching condition, during rapid quenching, the average temperature of whatever shape we're quenching is assumed to be constant. So this is a large plate, basically an infinite plate of a certain thickness. So we quench this plate very rapidly, and you get a temperature gradient on the surface that looks something like this. You have the interior at a high temperature, T high, and then the quench temperature, T low, is the surface. So you have a very steep thermal gradient on the surface, it's a very thin layer. So that's the rapid quenching condition. So the stresses that develop in this infinite plate are given by this equation here. Sigma S is the thermally induced surface stress. So that surface stress just equals the expansion coefficient of the material. A is the thermal expansion coefficient times E, the Young's elastic modulus, and then the temperature difference, the high temperature minus the low temperature. And for a plate, you have to incorporate the Poisson effect, so it's divided by 1 minus nu. So T high minus T low is just delta T. So the stress just equals the thermal expansion coefficient times the elastic modulus times the temperature change, and that's divided by 1 minus Poisson's ratio. So this is basically stress equal in the elastic modulus times the strain the strain is a thermal strain here, the thermal expansion coefficient times the delta T. And strains from thermal stresses can be quite high, can be much higher than strains produced on a sample from a mechanical test machine. The other situation is a gradual quenching. So in a gradual quenching, let's assume we have a constant cooling rate, phi. And again, we'll take a large infinite plate. And this diagram on the left is the cooling cycle. The one on the right is the heating cycle. So when you have a gradual quenching with a constant cooling or heating rate, you get these parabolic temperature profiles. So temperature increases in the upward direction. This plate has a thickness of 2 rm. And this would be the temperature profile for cooling. The surface is in tension, so Ts is the surface tension, the surface temperature. Ti is the interior surface, the interior temperature. And then Ta is the average of the two. So you can see the surface is in tension, the interior is in compression. The opposite takes place for heating. So now the temperature of the surface is higher than the temperature of the average, and the temperature of the center is much cooler than the surface. So now you have a compressive stress on the surface and a tensile stress on the interior. So these are opposites. The cooling cycle has a tensile stress on the surface, and then the heating cycle has a compressive stress on the surface. So the equation that describes that is basically the same equation. We just modified the delta T term. So again, it's gradual quenching, a constant cooling rate, phi. This is the equation describing the stresses. Sigma S is the thermally induced surface stress. Alpha is the thermal expansion coefficient. E is Young's modulus. T is temperature. Nu is Poisson's ratio. And then now we have to come up with a term for delta T, which is the average minus the surface. So that's TA minus TS. So for, again, gradual quenching at a constant cooling rate, the temperature differences that are developed in this plate, delta T, is given by this equation. So we said delta T is the average minus the surface temperature. So delta T is the function of the cooling rate. It's a function of the sample dimensions. Rm is half the thickness of the plates, so Rm squared. Each type of configuration has a different geometric constant. For a plate, it's 1/2. So C is a constant of 1/2 for a refractory in the shape of a plate. That's divided by K is the thermal conductivity, rho is the density, and Cp is the heat capacity. So we went over these thermal properties first day. So that's the equation for delta T, which you substitute back into the equation over here to give you the stresses that are developed on the surface. So when you do that, this is the equation that results for stresses in a large infinite plate at a constant cooling rate. So again, the thermal stress on the surface is a function of the thermal expansion coefficient, the elastic modulus, the cooling rate, the sample size, and the sample size is squared. So the bigger the sample, the bigger the stress. It develops a bigger thermal gradient. And then it's divided by the conductivity, the density, the heat capacity, the Poisson effect. And this is a 1/2 constant. that we talked about. So if you have a material that has high expansion, the higher the expansion in that material, the higher the stresses. High elastic modulus gives higher stresses. Faster cooling rate gives higher stresses. A bigger sample size gives higher stresses. If you're dividing by the thermal conductivity, the lower the thermal conductivity, the bigger the stress. So ideally, high conductivities do not allow for large thermal gradients to develop. And then the density and heat capacity are also in there. You don't have a lot of control over those. So for gradual quenching, here's the equations for other shapes. We're talking about, in our example, an infinite slab or an infinite plate. And that was the equations for the surface and center stresses. But these are other shapes: a thin plate, a thin disc, a long solid cylinder, a long hollow cylinder, a solid sphere, and a hollow sphere. So the equations are developed for all different types of sample shapes or refractory shapes. And then the temperature difference, in our case, we had an infinite plate of half thickness Rm. The equations for the temperature difference are over here. This is for a plate, a cylinder, well, infinite cylinder, a cylinder with a half length, and a cube. So these are the other equations. They just have different geometric constants. So you can take that same equation for different shapes and do the calculations and see what the stresses are. So there were two cases: rapid quenching and quenching at a controlled constant rate. But in real situations, you don't really have, you try not to have rapid, severe quenching, and your quenching rates are not always constant. So the surface temperatures do not change infinitely fast for a rapid quench, and cooling rates are not constant. So in that case, you have some finite time before you reach a maximum stress. So you have to look at another factor here called Biot's ratio. So that's beta equals Rm, which is half the thickness of the plate. We're still talking about a large infinite plate. H now is the surface heat transfer coefficient, and K is the thermal conductivity. This ratio is dimensionless. It has no units. So if we plot stress versus time, we get a series of plots for different ratios of beta from 0.1 up to 20. So the stress is just the surface stress that develops divided by a stress that would develop for an infinitely fast quench. So if we have a fast quench, the surface is going to, the stress on the surface is going to be the same as for an infinitely fast quench. So this number would be 1. So as we increase this stress number from 0, and they had to go to 0.8 here, that's going from a gradual to a very rapid quench situation. So what happens here, if we look at the ratio, Biot's ratio, so as beta approaches infinity, that's where we have the maximum stress occurring at time 0. So that's a very rapid quench. So as beta keeps increasing, and this graph stops at beta equals 20, but if it approaches infinity, this numerator here would be the same as the denominator, so we'd have an infinitely fast quench, and the stresses would develop instantaneously. If as beta decreases, the numbers decrease, the time to the maximum stress increases. So these vertical lines are the maximum in the stresses. So as beta decreases, it's a slower quenching, and then the time to the maximum stress actually decreases. Time to the maximum stress actually increases. It takes longer for the maximum stress to develop. And again, as beta decreases, the magnitude of the stress also decreases. So lower values of beta takes longer for the stress, maximum stress to develop, and the maximum stress is lower. So this ratio describes stresses that develop in transient conditions, basically where it's not a rapid quench or a gradual quench at a controlled rate. So beta equals Rm times H divided by K. Ceramics and refractories with high K have low values of beta, and low H, low heat transfer coefficients, have low values of beta. That produces these less severe thermal shock conditions. This just shows some examples of different values of the heat transfer coefficient, so you can get a feel for the range of that. If you have air flowing past the cylinder, and there are 4 different flow rates here, 0.025 pounds per second per a cross-sectional area, 1 foot squared, and that goes up to 60. So at 60 pounds per second per foot squared, and there's 2 units here. One's based on BTUs, one's based on calories. Let's just look at this one. It's 190. As you decrease the flow rate to 25 is 90, to 2.5 is 20, and to 0.025 is 2. Radiation from a ceramic type material that's at 1,000 degrees C is 26. Radiation from a temperature of 500 degrees C is about 7. If you subject refractory or ceramic material to water quenching, a very rapid quench, the heat transfer coefficient is very high, maybe between 1,000 and 10,000. And jet turbine blades are maybe 35 to 150. So you can see the difference between rapid quenching and a less severe condition where the heat transfer coefficient is much smaller. So that's how thermal stresses develop. And there's 2 approaches to designing a ceramic or a refractory to resist thermal shock. The first is thermoelastic theory. And that's an approach to design a material that totally resists any crack initiation. You don't want any cracks to initiate or grow, and you completely avoid failure, any type of catastrophic failure. In the thermal shock damage resistance approach, you allow cracks to grow, but you make them more, the crack growth is more resistant. So you build in a resistance to crack propagation, and you minimize the damage. You allow damage to take place, but you minimize it. So the first approach is not what you would use for a typical refractory material. It is something you would use for an advanced ceramic. If you're putting a silicon carbide turbine blade in an engine, you don't want any type of damage. You want to completely avoid a catastrophic failure. And the second approach is typical for refractories. So the thermoelastic theory, and there's a series of different R parameters, and this parameter R is for thermal shock resistance during a rapid quench. And we basically have developed the equation already for a rapid quench condition. We just rearrange it and put it in terms of delta T at failure. So for, again, our infinite plate, delta T at failure, the temperature difference required for failure equals the strength, which is the fracture strength, sigma F. Sigma F is the fracture strength, the Poisson effect, 1 minus nu, and that's divided by A, the thermal expansion coefficient, and E, the Young's elastic modulus. So delta TF, the temperature difference required for failure to take place, is known as the R parameter R. Other shapes, same equation, but now there's a S in this equation for a shape factor. So delta TF would equal R times some shape factor. So the thermal shock parameter R for rapid quench conditions, what do you need to have a high value of R or high delta T for damage to occur? Well, you need a high strength, you need low thermal expansion, and you need a low elastic, Young's elastic modulus. Unfortunately, most ceramic materials, the thermal expansion coefficient is not low enough to give a really high delta T. If you have a high strength material, that generally follows that the modulus is going to be high also. So that's a little bit of a problem here. Every time you have a high strength material, you're not going to have a low elastic modulus. So for two examples, I just picked a glass, a soda lime silica glass, which is just window glass. And we mentioned fused silica glass, which has the low thermal expansion coefficient. So both glasses have an elastic modulus of about 10 million PSI. Window glass has a strength of about 10,000 PSI. Fused silica is maybe a little bit stronger, 15,000 PSI. They both have the same Poisson's ratio, about 0.2. But window glass is typical of most refractory oxides. It's 10 times 10 to the minus 6 per degree C for the coefficient of thermal expansion. But fused silica is about 20 times less. It's 0.5 times 10 to the minus 6. So it has a much lower thermal expansion coefficient. So if you have a coefficient of expansion approaching 0, the material does not contract or expand when it's heated, so you cannot build up thermal stresses. So ideally, if you had an A equals to 0, you'd have a perfectly thermal shock resistant material. But this one comes pretty close to being 0. So if you calculate delta TF or R for this condition, 80 degrees C. So you only have to quench a window glass from high temperature to low temperature where the delta T is 80 degrees C, and it will fracture in a catastrophic manner. But for a fused silica glass, delta TF equals R is 2400 degrees C. That's not a realistic number. It's just a high number. Obviously, the glass will melt before it reaches 2400 degrees C, but it's just telling you that that glass is not going to thermal shock at all. So that's the approach for designing a material to completely resist thermal shock without any damage. It's not a good approach for a refractory, which is a very heterogeneous material loaded with microcracks. So you have to use this other approach, thermal shock damage resistance theory. And again, there's different parameters. Well, we'll look at two. We'll look at R4 prime and RST, and they both apply again to a rapid quench condition. So in the previous case here for thermoelastic theory, we're looking at rapid quench, the worst type of thermal shock. And in this theory, we're looking at a rapid quench condition. So we're just considering how you design a material under the worst conditions. So R4 prime and RST are appropriate here. So in this approach, the thermal shock damage resistance theory, the delta C critical, the critical temperature difference for crack to grow or propagate is given by this equation here. Gamma F is a fracture surface energy. We now have a fracture surface energy term. There's a Poisson effect. E0 is Young's elastic modulus. A squared is the thermal expansion coefficient. And we have a second term here that accounts for the number of cracks or microcracks in a refractory. N is the cracks per unit volume or the crack density, and L is the crack half length. So this is a rather long equation, but it really actually works. And the way it worked is you plot delta T versus the half crack length. And you have different graphs for different crack densities. So this would be N equals 100, N equals 10, and N equals 1. So you have a region in the upper portion of this plot that's the region of instability. And below that region, you have a region of stability. So if you have a crack of a certain length, let's say 10 to the minus 2 centimeters, and you're down with a temperature difference of a delta T of only 10, you're probably on the borderline of stability and instability, so you won't have any crack growth. So if you're in a region of stability, there's no crack growth. If you're in a region of instability, you have a crack propagation. So the solid line is a critical temperature difference for initiation of crack propagation. And depending on where you are on this region of instability, we'll show that in a few minutes. But depending on where you are, a crack may not arrest when it reaches this line. If it's moving in an increasing direction, it may arrest at this dotted line. So the dotted line is the crack length resulting from propagation of an initially short crack, and that short crack will have more stored elastic strain energy than a long crack. So let's look at the different conditions. If you're to the left of this minimum in the curve, you're going to have an initially short crack. So that crack is going to have excess kinetic energy. So it doesn't arrest until it hits the dotted line, and that's called kinetic crack propagation. So over here, to the left of the minimum, you have a short crack. You reach a delta T where that crack can grow, and it goes over, let's say it had an N equals 100, it'll arrest at this dotted line. So that's kinetic crack propagation, but you still arrest the crack and it stops. So you allow damage to take place, but your material is still intact. If you have an initially long crack that's to the right of the minimum, the crack will stop at the solid line, and that's known as quasi-static crack propagation. So those are the two situations. So for short cracks, R4 prime applies, and for long cracks, the other R parameter, RST, applies. So if you have a situation where you have small cracks, the thermal shock damage resistance parameter is R4 prime, and this is the definition of R4 prime. Gamma F is the fracture surface energy times the elastic modulus, and that's divided by the strength of the material squared, and then you have a 1 minus 2 nu for the Poisson effect. You want high values of R4 prime. That minimizes the damage and improves the thermal shock resistance. So to have a high value of R4 prime, you need a high fracture surface energy, a low elastic modulus, and a low strength. If you have a long crack, the thermal shock parameter is RST, and that's the thermal stress crack stability parameter. So RST again equals a fracture surface energy divided by, it's now divided by the thermal expansion coefficient squared and the Young's elastic modulus, and it's the square root of this term. So if you want a high value of RST to resist thermal shock damage, you need a high fracture surface energy, just the same for R4 prime, a low E, and a low thermal expansion coefficient. So let's apply R4 prime and RST to a material with a short crack length and see how it behaves. So again, delta T versus crack length. So let's say we have a crack of this length, somewhat lower than 10 to the minus 2 centimeters. So you have to increase the temperature, the delta T, in this region 1 until you hit the region of instability. So a short crack is going to propagate, and again, we'll take n equals 100 for the crack density. It's going to propagate past the solid line to the dotted line. So it's going to have kinetic crack growth. Now you arrest the crack, and yet now you have to increase the temperature difference again. So now you have to increase the temperature difference to this value over here. It's delta T is somewhat less than 100 on this plot. Then you're again in the region of instability, but now you're to the right of the minimum, so you're going to follow this curve. So 3 is the delta T necessary to start crack propagating again. 4 is the path of propagation, and that's where you have your quasi-static crack propagation. So that is what happens in these materials. You can plot this in a couple different ways. You can plot the crack length versus the temperature difference. So we're just reversing the axes here and looking at it in a little different way. So let's say you have an initial crack L0, and now you increase the delta T, so you have a delta T critical. So increase the temperature, all of a sudden you have kinetic crack propagation, and the crack grows to a new length and arrests. That's region 2. Now you have to increase the delta T again to a new critical difference, delta T critical prime. And then the crack grows. Well, the crack is constant until you reach the delta T critical prime, and then you're in this region for quasi-static crack propagation. So that's how the crack length changes with temperature difference for a refractory type material. Since crack length is proportional to strength, we saw that through the Griffith equation, you can plot strength versus delta T. And this is something that you can measure rather easily. You can thermally shock samples and you can measure their strength, thermally shock them at different delta T's and measure the strength. And you'll get plots that look like this. So let's say we have an initial strength at 0. We increase the delta T so we have a critical temperature, and then we have the instantaneous decrease in strength as the crack propagates. It arrests. And then we have to increase the temperature to another critical delta T, no change in strength. Then all of a sudden we have a gradual strength decrease. So this is the way you want to design a refractory. You want to allow the cracks to grow and stop and arrest and to grow in a very stable manner. Ideally, you want to avoid any type of kinetic crack growth and have this curve here start right here and just have a gradual failure the whole time. So you can allow a lot of damage to take place in a refractory before it actually fails. So if we compare R and R4 prime, R is proportional to the strength over the elastic modulus. R4 prime is proportional to the elastic modulus over the strength. So they're completely opposite. So you cannot maximize for both a resistance to fracture initiation and crack propagation. So R applies to a high performance technical ceramic, which is a high strength material where you completely want to avoid any type of crack initiation and strength degradation. And then R4 prime applies to the refractory type material. So you can make measurements on different kinds of materials, and this is strength versus temperature. And there are 4 plots on this diagram. This material has a grain size of 10 microns. This one is 34 microns. This is 40 microns, and this is 85 microns. So something up here might resemble a refractory type material. You have a low strength material, less than 10,000 PSI. And this type of material would be in advanced ceramics, maybe a high performance silicon carbide. You might have a strength greater than 100,000 PSI. So if we start out at the bottom here, your advanced ceramic, if you thermally quench it, and this temperature is 200 degrees, see you get a rapid decrease in strength. And then we follow the pattern which we just illustrated on a previous slide. We have to increase the temperature to another delta T and you have a gradual failure. So you have a large drop in strength here. As you go up in grain size, this vertical drop in strength keeps decreasing. And finally, at this point, you don't see that rapid drop in strength anymore. You just have a gradual strength loss. So this is how you want to design a refractory. You want to avoid any type of catastrophic loss in strength and just have a gradual strength loss. So the shapes of these curves are exactly the same as this, which is exactly predicted by theory. So that theory that describes thermal shock damage resistance really works rather well. So if you're designing a refractory, you want to start with the crack length at the minimum in the delta T versus L plot. If you do that, you'll get this gradual strength loss and avoid any type of more rapid strength loss or catastrophic strength loss. You can control that by the size of the flaw. And we mentioned that the grain size, because of the thermal expansion mismatches, the grain size is the flaw size. There's a microcrack generated around the grain on the order of its size. So a greater flaw, you can put in bigger flaws by putting in bigger grains. You can control the number of cracks or flaws by introducing different types of inhomogeneities in the material pores. I mentioned that most refractories that are just a sintered refractory are going to have 10 to 20 cent porosity, and they're microcracked. So by controlling the grain size and the number of grains, the grain size distribution, you can control the flaw size and the number of flaws. The other term in the equation that we looked at, either R4 prime and RST, that's important, is the thermal expansion coefficient. It's in the denominator of the critical temperature difference equation. So again, if you have a 0 thermal expansion coefficient, you do not develop any stress level when you change the temperature. A low thermal expansion coefficient, you only develop low stresses as you change the temperature. And if you have a high thermal expansion coefficient, obviously you can develop high stresses with delta T's, temperature changes. Most refractories are going to be in this high category, around 10 to the 12 to 13 times 10 to the minus 6 per degree C. And I just showed you a fused silica, which is 0.5 times 10 to the minus 6 per degree C. The only problem with fused silica, it's only good to a low temperature for a refractory material. 1,000 degrees C is pretty low for any application. And we showed some thermal expansion behavior for different materials 2 days ago. So this is for simple oxides, and this goes from 0 to 2% linear expansion from about room temperature to 2,000 degrees C. Here is vitreous silica or fused silica. You can see how low it is, but relative to that material, all these other oxides are quite high. MgO is the highest, CaO is not that much different. And here's ZrO2 and Al2O3 and quartz and Cr2O3. So they're all fairly high. So you don't have much choice. You really can't lower the thermal expansion coefficient. And then when you get more complex refractory oxides, binary and ternary oxides, we have some different materials here, like we have mullite, zircon, the spinel, and they're still, this is still 0 to 2, so they're all still pretty high. On here is another material known as cordierite, which we mentioned the first day. It has relatively low expansion, but again, it's only useful to about 1200 degrees C. So you really can't adjust A in these materials to get a more desirable situation. You have a little more choice when you look at non-oxides. Again, it's the same scale, 0 to 2 versus temperature. So these are a little bit lower. So materials like silicon carbide and graphite, amorphous carbon, you have a little bit better chance to design them into a refractory material with a lower expansion coefficient to improve the thermal shock resistance. So the other term is the fracture surface energy, and that was in the numerator of the critical difference equations. So how do you control the fracture surface energy? Many years ago, it was believed that this fracture surface energy was the thermodynamic surface energy, which is just the energy necessary to create a unit area of new surface on the order of 0.1 joules per meter squared. So any surface has excess energy relative to the bulk of the material because of the unsatisfied bonds, and that's the thermodynamic surface energy. But in this equations that we have R4 prime and RST, it is not the thermodynamic surface energy. There's actually 3 different types of surface energies that we need to consider. There's one called gamma NBT, which is from a notch beam technique. It's not this surface energy. This is the surface energy needed to start a crack growing. So that's quite a bit higher than the thermodynamic surface energy. It's about 10 joules per meter squared. So we have a thermodynamic surface energy, a crack initiation surface energy, and then we have a surface energy that is necessary to propagate a crack. So that's gamma WOF, which is work of fracture. So this surface energy is what is in those critical equations. So the effective surface energy is gamma WOF, is the energy necessary to propagate a crack. So that's the energy necessary to keep a crack growing. And that accounts for crack microstructure interactions. And it's a much higher number than either of the other 2 surface energies. It's about 80 to 120 joules per meter squared. So when you design a refractory to resist thermal shock, you're designing a refractory microstructure to resist crack propagation. And there's different ways of doing that. It turns out a crack has a frontal process zone and a crack wake. So you can design a microstructure for either one of these regions. In a frontal process zone, you might want to design a zone where you have microcrack extension. You might want to allow for crack branching or crack deflection around a particle. Or in the crack wake, which is probably the most important zone for thermal shock resistance, you would design in crack bridging. So this is what a crack looks like running through a refractory material. And the process zones in the front of the crack tip, this is the frontal process zone. In the wake of the crack, this is the wake region, or the zone behind the crack. There's a great deal of stress at the crack tip. That stress forms microcracks, or it causes existing microcracks to grow longer, and maybe you develop crack branching. But you're dissipating a lot of energy by forming all these crack surfaces in the frontal process zone. In the wake region, the crack is growing, it's opening up. This is the surface of the sample. CMOD is a crack mouth opening displacement. It's the width of the crack. Here we have coarse aggregates bridging the crack. You can also put in fibers to bridge the crack. We also have, at high temperatures, we may have some viscous silicate glasses bridging the crack. So what's happening behind the crack tip in the crack wake is what we believe is really controlling the thermal shock damage and controlling the way this crack propagates. So we can measure these fracture surface energies. Gamma NBT, which is the single edge notch beam, or gamma WF based on the work of fracture. And they're measured in simple 3-point bending beams. And here's a 3-point bending beam, the lower knife edges, the top knife edge where the force is applied. The span would be L. And we'd have a straight through notch. So it's called a single edge notch beam. So F is the force, L is the test span, B is the width of the sample, H is the height of the sample, and C would be the depth of this crack. So we just load this to failure, and then we get this term gamma NBT, which is the fracture surface energy necessary to start that crack moving. It's a rather complex equation based on stress intensity factors, but all you need to do is measure the load, the span, the crack depth, the sample dimensions, B and H. You need the elastic modulus and the Poisson ratio to be measured independently. And then this term is a function of sample dimensions C over H, which is then a function of these other constants. The constants are shown here. This term is a function of C over H. And then these constants are a function of L over H. So you can measure all of these parameters and calculate this number by running a simple notch beam type sample. The other fracture surface energy necessary to keep the crack growing is the work of fracture. And there you have a chevron notch beam. So you cut away the sample to leave this triangle ligament. So A is the area of this ligament, and you cut away the two triangles on either side of this inverted triangle. Same type of arrangement, a simple 3-point bending. The lower knife edges, you apply a force in the center. W is the width of the sample. H is the height of the sample. And A is the area of this triangle. That's the ligament that's holding the sample together. So what you do is you fracture this in a very slow manner. In this sample, you fracture it rather quickly at a fairly high rate of speed because you want catastrophic failure. In this experiment, you fracture it at a very slow speed to get a stable fracture. So force or load versus displacement X. You load it, then the crack starts growing in a very stable manner. And the longer this tail, the more crack bridging in the wake of the crack. So the area under this curve is the fracture surface energy. So gamma work of fracture just equals the integral of f dx, which is the area under this curve, divided by 2a. A is that triangle right here, the bridging ligament. You create two surfaces, so you have to have a factor of 2 here. So this experiment, if you run it correctly, sometimes it takes an hour or more to generate this curve, but you get the entire work required to propagate a crack through a sample. So what you can look at after you measure these surface energies is the ratio of the work of fracture to the notch beam technique. Refractories that have good thermal shock resistance are going to have a large value greater than 10. So there's a high energy consumption during crack propagation relative to the energy needed to start a crack. Refractories are full of microcracks. It doesn't take much to start them moving, but you want to make sure when they start moving, it requires a lot of energy to keep them moving. So you need a high ratio here. So the higher the ratio, the better thermal shock resistance. Refractory is able to accommodate extensive internal cracking and still remain intact. So you start out with a weak material, you keep making it weaker and weaker, but you do it in a controlled manner so that it still has mechanical integrity. Even though it has low strength, it's still in one piece and it's surviving whatever application you're using it in. So the higher the ratio, I mentioned that it relates to the extent of the long tail portion of the stress strain curve or the load displacement curve. So the longer this tail is, the better off you are, and the bigger this difference is going to be. So again, here is the what happens. You're going to develop a steady state frontal process zone. So this stress concentration is the same in the frontal process zone. It doesn't change as the crack moves forward. So you have a steady state frontal process zone, and you can dissipate energy by forming cracks in the frontal process zone. The wake region continues to increase in size. As the crack propagates, the wake region gets longer and longer as the crack gets longer and longer. And that's what continues to increase the resistance to crack growth, what happens in the wake of the crack. So it's more important to crack growth resistance than what's happening in the frontal process zone. And that's what extends the tail in the work of fracture test to long times. In a refractory, this opening, the crack mouth opening displacement, will be quite large. In a high strength ceramic, it's going to be very small. You're not going to have this type of bridging. You're going to have a short crack that's going to fail at a high strength rather catastrophically. So the crack mouth opening displacement, small and brittle ceramics, but large in refractories because of all the bridging that takes place in the crack wake. So crack process zones, aggregate bridging. There's different ways you can do this. So there's at least 3 possible mechanisms, and they all require aggregates that are stronger than the matrix, and that's typically the case in refractories. You have fired aggregates in a weaker matrix. The matrix is the weakest point. You can have aggregate bridging across fracture surfaces. You can have aggregates wedging behind the crack in conjunction with the bridging. And you have frictional effects. Cracks have to pull out of the matrix. So there's a frictional pull out effect of the aggregates from one side of a passing crack. If the aggregate is a fiber, you then have to pull the fiber out of the matrix, which is a greater frictional effect. Silicate bridging, I mentioned, that only occurs at elevated temperatures where you have a glassy silicate. And it's a viscous silicate and can flow enough to form bonding ligaments across the crack surfaces. And that's active only over only a limited temperature range. So it's not active at low temperatures. As you increase the temperature, you'll have a viscous silicate. If you keep increasing the temperature, it becomes less viscous and fluid, and you don't have bridging ligaments anymore. So it's active over a limited temperature range. Once the temperature becomes too high, the viscosity decreases and the bonding ligaments disappear, and they're no longer contributing to dissipating energy in the crack wake. So opportunities for improving crack growth resistance by designing the microstructure, aggregate size. You have to have aggregates bigger than that crack mouth opening displacement for bridging to take place. Aggregate geometry. So angular aggregates have better mechanical interlocking than an aggregate that's more spherical in shape. So angular aggregates are better in terms of their interlocking with the matrix. Fiber additions have large aspect ratios, long length relative to their diameter. So fibers are a very effective way of energy dissipation in a crack wake. Other possibilities, aggregate strength. Strong aggregates are better than weak aggregates, so you increase the aggregate strength. Aggregate surface texture. Rough surfaces are better than smooth surfaces. There's more interlocking with the matrix. And then the chemical bonding between the matrix and the aggregates. If the bonding is very strong, you're not going to have, you're going to deactivate, you're not going to have these bridging mechanisms. Fracture isn't going to go around the coarse particles, it's going to go through them. So if the matrix has the same strength as the particles, you're defeating the purpose here. You're not designing a microstructure that resists thermal shock resistance. So that's a little bit of background on the approach to designing a microstructure for a refractory that'll resist thermal shock. And I think well, we still have a half hour before break, but we'll go over this test here. It's ASTM C1171. It's really the only thermal shock test that is offered by ASTM. So what you do in this test is you determine the strength loss or reduction in structural continuity of a refractory subject to some type of thermal cycling. You can measure the strength loss, so the difference in flexural strength, and the three-point bending is just called modulus of rupture. So the difference in flexural strength between an uncycled sample and then a sample that you thermally shock. And you can measure the reduction in structural continuity. And we talked about a sonic velocity measurement. We talked about a Young's modulus measurement. And we described the equipment and experiments needed to make these measurements. So you can measure the before and after sonic velocity or the before and after Young's modulus, and that's before and after thermal cycling. So when you thermally shock a material, the cracks grow, they become bigger cracks, you'll have a strength loss. So you can see the amount of damage by the loss in strength. But also when cracks grow, become bigger, the velocity of sound decreases. Also, the Young's modulus decreases. So both of these measurements, a decrease in either one, measures the amount of damage that's takes place. This is a destructive test. You have to break the sample. These two tests, like as we mentioned, are non-destructive. So 3 different other experimental techniques you can monitor the thermal shock damage. The importance of the test, well, it indicates the ability of a refractory to withstand a stress generated by a sudden change in temperature. You use it for research and development to make improved products, and you can compare products. If you have an application where you think there's going to be thermal shock damage, you can use this test to evaluate a range of products to see which will perform the best. This test is done on a 1" by 1" by 6" sample. And here's a typical 6" sample. You can run this test on a fired brick. You can run it on an unfired castable, for example, but you have to pre-fire it to a temperature at least as high as the thermal shock test temperature. Otherwise, you'll be measuring other changes in the material where it's densifying. You don't want to measure any other changes. You want to just measure thermal shock. A really simple test. You just need a furnace, and the test is run at 1200 degrees C. The standard test, you could run any temperature you want, but the ASTM test is 1200 degrees C. You need a mechanical test machine, whether it's hydraulic or mechanical, to measure the strength. You need equipment to measure the sonic velocity and equipment to measure the elastic modulus. So what you do is you measure the sonic velocity, Young's modulus, and bulk density on a group of 10 samples. And you divide those samples into 2 equal groups based on sonic velocity, Young's modulus, or bulk density. So you take one of these test methods and rank them from lowest to highest, and then you take every other one and divide it into 2 groups. So the control group, you measure the strength on the 5 samples that are the control group. So you already have the sonic velocity, the bulk density, the Young's modulus, all non-destructive tests. Then you fracture those 5 samples. So that establishes your baseline data. The other group of 5 samples, you cycle them in a furnace. So you put the samples in the furnace at 1200 degrees C for 15 minutes. You pull them out of the furnace. You cool it, air cool it for 15 minutes. If you wanted a really severe quench, you can drop them in water for 15 minutes. And you just repeat the cycle 5 times. Insert them in the furnace at 1200, hold 15 minutes and pull it out, and either air quench it or perhaps you may water quench it. You do that 5 times. Now on these samples, you measure the sonic velocity, the Young's modulus, and the strength. So now you get your data on the cycled samples. And then you just calculate the loss in either sonic velocity, Young's modulus, or the strength. So for the sonic velocity, you have your initial unshocked samples, V0, and then you have your shock samples, VF. So the initial sonic velocity minus the final after shocking divided by the initial times 100 gives you the loss in sonic velocity. The Young's modulus is just the E0 modulus of unshocked samples minus the modulus of the shock samples divided by the initial modulus of the unshocked samples. You multiply that times 100 and you get your Young's modulus loss. And the strength loss, M0 is the modulus of rupture of the unshocked samples minus MF, which is the modulus of rupture of the shock samples. And you divide that by the initial strength before shocking times 100, and you get your percent strength loss. So 3 different ways of characterizing the damage. And so when you make this measurement, a report would look something like this. This first group on the top are your control samples. And this must have been in some type of castable because it was pre-fired at 1200 degrees C to stabilize it for the 1200 degrees C quench test. So samples were labeled 1 through 10, and these were the samples that were pulled out for one group, and then these are the samples that are pulled out for the other group. But you just measure the dimensions, length, breadth, and depth. You measure the weight. We talked about using a grindosonic to get a frequency for an elastic modulus. So you make a frequency measurement for Young's modulus. There's a V meter to measure the sonic velocity. This is in microseconds. There's your constant to calculate the elastic modulus. So you calculate the modulus, the sonic velocity, the density, and here we load it. These are the control samples. You load it to failure, and then you get your MOR or your strength data. So you get an average Young's modulus, an average sonic velocity, an average bulk density, and an average strength. And then you take your test group, which are the samples you thermally shock, and you do all the non-destructive measurements on them. You measure the dimensions, you measure their weight, you do the measurement for the Young's modulus, you get the frequencies of vibration, you do the measurement for sonic velocity, and you get the velocity. And then you get well, actually, this is the microseconds, the time your velocity is calculated down here. So you get a calculated modulus, velocity, and density. Modulus and velocity, again, are non-destructive. So now you have another average here for modulus and velocity. And then you thermally cycle these 5 samples. They went through 5 cycles at 2190 degrees F in a gas kiln. And then you measure the same measurements, the length, breadth, depth, weight, the frequency of vibration, the time for the waves to the sonic sound waves to travel through the sample. You have your constant, you calculate the Young's modulus, the velocity, the density. You get a Young's modulus change. And in this case, it was 54%. So the modulus decreased by 54% after shocking. The velocity change was minus about 33%. You measure the strength after you do the non-destructive test. And the strength actually decreased about 82%. So these percentages aren't going to be the same for each type of test, but they're all relative. So 82% decrease in strength is not the greatest material for thermal shock resistance, but it's still intact after some fairly severe thermal shock testing. So that's the section on thermal shock and the test that you can use to measure thermal shock. Does anyone have any questions on that? So we have a little bit of time before 12:30. The next section is a little longer. It's on corrosion. And maybe we'll go through this or get started on the first section here, fundamental principles of liquid-solid corrosion. And then after lunch, we can discuss liquid phase formation, wetting. If you have a slag or metal in contact with a refractory, if you have a non-wetting condition, if it doesn't wet the refractory, you're not going to have a corrosion reaction. So wetting, characterizing wetting is important. And then phase equilibrium diagrams, that's going to tell you what kind of reactions take place. And then we'll go over some laboratory corrosion type tests. So the first thing, we'll look at some of the fundamental principles of liquid-solid corrosion. So to define corrosion, it's simply refractory wear by loss of thickness or mass from an exposed surface of the refractory as a result of some type of chemical attack by a corroding fluid. That could be a slag, could be glass, could be a metal. So you're removing material by a chemical reaction. The refractory and the corrosive fluid react. And at the hot phase where this reaction is taking place, you're approaching a localized chemical equilibrium right at the zone of contact between the refractory and the fluid. And I mentioned that refractories are heterogeneous. They're not at thermodynamic equilibrium, but at high temperature, at that interface with the corrosive slag, glass, or metal, any other fluid, you are approaching a chemical equilibrium. We can look at phase diagrams, or we can look at kinetics. So phase diagrams are a type of chart or map that show the conditions at which thermodynamically distinct phases can occur. So it's going to tell you what kind of reactions are going to occur with those chemical compositions at a particular temperature. So you use it to analyze corrosion conditions and predict a chemical strategy to minimize the wear rate. So phase diagrams are based on thermodynamics, and they're just going to tell you what's going to happen between the different chemical species, what's going to react, maybe what compound you might form, maybe what liquid phase you might form, but it tells you what's going on at the hot phase. Kinetics are models that describe how fast that reaction takes place. So they yield information about the chemical reaction mechanisms. So phase diagrams are going to tell you what reactions are going to take place, and kinetics are going to tell you how fast they take place. So when we're talking about corrosion and we're looking at phase diagrams, we want to look at reactions that form low melting compounds. The low melting compounds are just going to give rise to corrosion. So if there's no chemical effect, you have a material system that melts at a higher temperature than the use temperature. So whatever process you have with the refractory in contact with the fluid, if the system melts at a higher temperature than whatever temperature you're running your reaction at, you're not going to have a chemical effect. On the other hand, you'll have a chemical effect when the material system melts at a lower temperature than the temperature you're operating at. At that point, you develop a liquid system and you'll dissolve the refractory into the corroding fluid. For kinetics, a reaction depends on the rate of formation of these low melting compounds. And the rate of formation of a low melting compound is going to depend on the temperature, the slag viscosity, the slag velocity over the hot phase, diffusion rates of species into the refractory, and the surface area of the refractory. High surface area gives rise to higher corrosion rates. That's why in glass tank, they line the part of the tank that's in contact with the glass with a fused cast refractory, which we'll discuss later, but it basically has no porosity. So to minimize the chemical effect, the rate of formation of low melting compounds is low. If you have a maximum chemical effect, the rate of formation of low melting compounds is high. So what happens during refractory corrosion? You have a corrosive fluid or a slag that contacts the refractory hot phase at some elevated temperature. You have a thermal gradient in the refractory wall from hot phase, which is the highest temperature, to the cold phase, which is the outer surface, which has the lowest temperature. So you have a temperature gradient across the refractory, and that establishes a freeze plane for the slag. So a freeze plane is a temperature that's low enough to freeze the liquid slag. So that's somewhat behind the hot face depending on the thermal gradient. So the slag may penetrate a certain distance into the refractory, hit a temperature low enough so it'll freeze solid. So that's your freeze plane. The slag reacts with the refractory at the hot face, forms new phases. It also penetrates through the pores and reacts behind the hot face until it gets to the freeze plane. Some cases, what may occur during refractory corrosion is you might have two distinct slag layers. You might have a fluid outer slag layer that is the unaltered slag, and you might have an inner slag layer in contact with the hot face that's more viscous because it's been altered by the refractory. So some of the refractory has dissolved into the slag, and generally that increases the viscosity of the slag in contact with the refractory. So this is a cross-section, a schematic drawing. This is the slag refractory interface. This is the inner slag layer. It's the more viscous layer, and there's small particles of undissolved refractory in that, but it is more viscous. And this is your outer slag layer that is more fluid, and this shows the slag flowing in that direction of the arrow. This solid line is the slag freeze plane. So slag penetrates till it reaches the freeze plane. It'll go through pores, and the material may be diffusing inward also by diffusion process. And these little lines along the surfaces are where chemical reactions are taking place. So there are three fundamental principles of corrosion, refractory and slag compatibility, porosity and corrosion rates, and reactions and thermal gradients. And I think we may have enough time to go through these before break. So refractory and slag compatibility, we'll at least get through acids and bases. So acids and bases in corrosion chemistry at elevated temperatures. So refractories are either they're either acids, bases, or neutral. So acidic refractories tend to resist acid slags better than a basic slag. Acids and bases react, so you don't want to put a basic slag in contact with an acid refractory because there'll be a reaction. Also, basic refractories tend to resist basic slags better than acidic slags. You don't want to have a basic refractory in contact with an acidic slag. So an acid refractory might be SiO2. You don't want to put it in contact with a high lime containing slag, which is a basic slag. A basic refractory might be MgO. You don't want to put it in contact with a high acidic slag, which might be high in SiO2. So how do we define acids and bases in corrosion chemistry at elevated temperatures? An acid material contains an excess of silica, SiO2, over a basic material, and a basic material contains an excess of calcium, CaO, over magnesia. Either one of these are both basic over an acid material. So if we set up a simple ratio of these components, CaO plus MgO divided by SiO2, neutrality is defined as a ratio of 1. If we have excess basic material, CaO or MgO, we'll have a number greater than 1, so it'll be basic. If we have excess SiO2 and the ratio is less than 1, it'll be acidic. That is a very simple approach to defining an acid and a base, but you can refine that with something known as a V ratio. So the V ratio, if it's greater than 1, your chemistry is basic. If it's less than 1, it's acidic. So this is an expanded version of the previous simple version where you have additional components. So in the numerator, we have the basic components, CaO, MgO, FeO, MnO, and so on. In the denominator, we have the acidic components, SiO2, P2O5, Al2O3, Fe2O3, and Mn2O3. So you get the percentages of each one of these components in your chemistry, and you see if the ratio is less than 1 or greater than 1. If it's greater than 1, it's basic. If it's less than 1, it's acidic. And there's no, I'll talk about basicity later on, but there's no great way of measuring this. But there's an empirical table here which ranks these materials from acidic. And then I had to move the table over this way. It continues all the way to basic. So you can see on the basic side, here's MgO highlighted. It's a basic material. SiO2 would be acidic. We mentioned P2O5, that's all the way up here, that's very acidic. Alumina, sometimes people call it acidic, but it tends to be in the middle. It's actually, I believe, more neutral than acidic, so it's Cr2O3. So this is ranking these materials from acidic to basic. So when you use this equation, you have to put the different percent of these different compounds in based on a table like this. Basically assuming everything below alumina is basic, everything above alumina would be acidic. Okay, I think what we'll do is we'll stop here and then go through the rest of this lecture. So I think we're about halfway through. So I'd like to get started again. So we were in the middle of corrosion testing, and we had just defined some equations for how to differentiate acids and bases in refractory corrosion. I think on the last lecture, when I talk about design, I'll talk about something called optical basicity, which is a better way of ranking the acids and bases, putting an exact number on them that you can use in those calculations. But anyway, defining acids and bases in corrosion. Corrosion is simply an attempt by the system, which is the slag in the refractory or whatever fluid and refractory you have, to achieve compatibility by moving towards thermodynamic equilibrium. And I've mentioned several times that refractories are not at equilibrium on the microscopic scale because of their heterogeneous nature. But on a localized level, at the immediate corrosion interface between the refractory and the slag, so right at the hot face between the refractory and the slag, the reaction is approaching equilibrium. It's a fluid slag and it's at high temperature, so reactions can take place rather quickly. So porosity affects the corrosion rate. Refractories contain open pores that can be penetrated by a fluid. So the open porosity in a refractory is 10 to 20%. Normally in a refractory that's been sintered or fired. There's also closed pores on top of that. So the fluid penetrates the refractory, causes destructive reactions behind the hot face. And usually the matrix is the more porous region, so that usually the destruction takes place in the matrix. It contains more impurities, more porosity than the coarser aggregates. And in the extreme case of corrosion, you erode away the, you dissolve the matrix and the unreacted aggregate is removed through the slag. The corrosion rates increase linearly with the percent of open porosity, and apparent porosities are, like I said, usually less than 20%. Temperature gradients affect how the slag reacts with the refractory. You can have a steep thermal gradient or you can have a broad thermal gradient. So if you have a steep thermal gradient, maybe you have a thin wall that's water cooled, a thin wall refractory that's water cooled, you have a very steep gradient, a little slag penetration, the freeze plane is near the hot face. Corrosion reactions are restricted to the immediate slag and refractory interface, and the slag penetration is usually less than a millimeter. If you have a broad thermal gradient, you can have significant slag penetration and materials diffusing into the refractories and causing reactions. And that penetration depth can be much larger, maybe 150 millimeters. So a steep thermal gradient would be a thin wall refractory lining a vessel with water cooling. And there's different stages of slag attack. For stage 1 slag attack, in this case, in a steep thermal gradient, there's little or no slag penetration. Any corrosion reactions that are taking place are right at the slag and refractory interface. And this is a schematic diagram of stage 1 slag attack. This is the slag, and the refractory are the coarser aggregates plus the matrix, which are the finer aggregates in this drawing. And this would be the interface between the slag and the refractory. So there's some surface reactions on some of the coarser particles, a little bit of slag penetration into the matrix and reaction with the coarser particles in the matrix. So in stage 1 slag attack, the hot phase temperature is what's really controlling the rate of corrosion. So if the hot phase temperature is just below the point where the reaction products become liquid, then corrosion is very slow. So there's two ways of looking at this. If the hot phase is maintained at no more than 20 degrees above the lowest eutectic temperature, then the corrosion rates are quite slow. But if the hot phase is maintained at more than 20 degrees above the lowest eutectic temperature, you have rapid corrosion rates. So the eutectic temperature is the lowest melting temperature in the system. So if you're slightly above the lowest melting temperature, the corrosion rates will be slow, but if you're significantly above the lowest melting compound, then the corrosion rates will increase. So the other condition, a broad temperature gradient, would be a refractory wall that's very thick. You start out with stage 1 slag attack. You have initially little or no slag penetration, and corrosion reactions again are restricted to the slag refractory interface. But over time, because the thermal gradient is very broad and the freeze plane is farther behind the hot phase, you go into stage 2 slag attack, where you have more extensive corrosion. You have extensive slag penetration. Reactions are taking place at the refractory hot phase, and you're now disrupting the microstructure of the hot phase. So this is a diagram for stage 2 slag attack. Again, this is the initial interface between the slag and the refractory. The slag is on the left, the refractory is on the right. You can see now that the slag has substantially penetrated the matrix. It's attacking the coarse aggregate. There's a chemical reaction at the surface of the coarse aggregates. The finer aggregates are dissolving, and some of them are reacting and floating into the slag. So the hot phase here is substantially disrupted in stage 2. So what can happen sometimes in stage 2 slag attack is you can have something known as densification spalling. So you have a slag penetrated layer at the hot face of the refractory, and that slag penetrated layer now has different properties than the bulk of the refractory. It'll probably have a different thermal expansion coefficient than the original refractory. So the slag penetrated region is now different than the original refractory in terms of its thermal expansion coefficient. If this application is one where there's thermal cycling, where the temperature is cycled from, say, hot to cold conditions, you can thermal shock that layer because of the thermal expansion mismatch. So spalling can occur as the temperature is cycled. You go through these heating and cooling cycles. So if that layer that's reacted or penetrated spalls off, you go back to stage 1 slag attack until you develop another dense layer, with different properties, and then stage 2 starts again. So that can occur over and over again until the refractory is completely spalled off. If you have no densification spalling, then you go into stage 3 slag attack. So now the refractory bonding at the hot face is minimal. Basically, the matrix is gone. The slag is now the continuous phase holding the coarser particles together. And you have a high viscosity slag in contact with the refractory because you're dissolving the high temperature material or the refractory into the slag. So this is what stage 3 slag attack might look like. It's hard to recognize the original refractory, but there's relics of the coarse material. Some of the medium-sized aggregates are floating into the slag, and there's complete penetration and dissolution of the matrix. So that's a little bit about acid-base reactions and how the slag or any fluid attacks the refractory. Another aspect that's important is wetting. And I mentioned earlier that if a slag or any other fluid does not wet the refractory, it can't react with it, so it can't corrode it. But that's not usually the case. So we need to talk about wetting of a solid by a liquid. So we consider the surface and interfacial energies. So surfaces and interfaces have higher energies than the interior bulk of the material because of unsatisfied bonds and so on. So if we take a refractory and let's say we have a drop of or a portion of slag on top of that refractory, and it's at a high temperature, so it conforms to this shape. So now we have slag sitting on top of a refractory. If the slag completely spreads, it's complete wetting. So now we have a thin layer of the slag on the refractory, there's wetting, and now you can have a reaction between the slag and the refractory. So here's an intermediate case between this one and this one. This may be termed more approaching non-wetting. This was completely wetting. And we can describe this angle, theta, is the tangent to this spherical shape where it meets the refractory. So that's the angle theta, and it's a measure of the wetting. There are 3 surface energies or interfacial energies involved here. There's a gamma liquid vapor. So that's between the liquid slag and the atmosphere or the vapor. There's a solid liquid that's between the slag and the refractory. And then there's a solid vapor between the refractory and the atmosphere. So those interfacial or surface tensions can be represented by vectors. And if you sum the vectors in the direction of the interface between the slag and the refractory, you end up with an equation that looks like this. So the cosine of this angle, the contact angle theta, equals gamma SV, the surface energy between the refractory and the atmosphere, minus gamma SL, the interfacial surface energy between the refractory and the liquid slag, divided by gamma LV, the surface energy between the liquid slag and the atmosphere. So this is the equation. Gamma LV times cosine theta equals gamma SV minus gamma SL. Or the way I had it written on the previous slide, cosine theta equals gamma SV minus gamma SL divided by gamma LV. And again, the SV is the solid vapor interfacial energy, the SL is the solid liquid interfacial energy, and LV is the liquid vapor interfacial energy. All of these interfacial energies have the units of ergs per cubic centimeter, ergs per square centimeter. So the equilibrium shape in this situation confirms to the minimum interfacial energy. And another way of just looking at this is defining what's called the spreading coefficient. So when the cosine of theta equals 0, that actual number is 1, but when theta equals 0, you have complete wetting. So just solving the equation, putting in 1 for cosine of theta, you can have an equation LS, which is a spreading coefficient, equals gamma SV minus gamma LV minus gamma SL. So S has to be positive for wetting to occur. And to have wetting, you have to have these conditions also. This surface energy gamma SV has to be greater than gamma LV, and also gamma SV has to be greater than gamma SL. So for corrosion reactions to take place, wetting must occur, and we're defining wetting at an angle less than 90 degrees. So if theta is less than 90 degrees, we're saying we have a degree of wetting, but as theta approaches 0 degrees, we have complete wetting. So there's some general rules concerning this. Wetting is most effective when the type of chemical bonding is the same in both the liquid and the solid. So we have ionic bonding for oxides, covalent bonding for the non-oxides, and metallic bonding in the metals. So if you have an oxide slag in contact with an oxide refractory, you're most likely going to have wetting. If you have an oxide slag in contact with nitride or carbide, you're going to limit the amount of wetting. So liquid metals do not effectively wet either oxide or non-oxide refractories, and liquid oxides do not effectively wet non-oxide refractories. And this would be the case of actual refractory, perhaps in the hot phase, where it's undergoing attack by a slag. Here we have 3 grains of a refractory material, and in between them is a liquid phase. There's an angle here, phi, that's a dihedral angle. So in this case, we have a gamma SS, which is the interfacial energy between 2 solid grains, and we have a gamma SL, which is the interfacial energy between the solid and the liquid slag. So the equation that describes that is if you solve in a direction parallel to this vector here, gamma SS, you get gamma SS equals 2 times gamma SL times the cosine of phi over 2, or this ratio, gamma SS divided by gamma SL just equals 2 times the cosine of phi over 2. And again, gamma SS is a solid-solid interfacial energy. Gamma SL is a liquid solid interfacial energy, and that's in ergs per square centimeter. So we can look at this angle, the dihedral angle versus how the phases are distributed. So if the dihedral angle is greater than 120 degrees, that means that gamma SL is greater than gamma SS, and the liquid phase is now in the form of isolated pockets. So here's an example where the dihedral angle is 135 degrees. You have your solid grains, and now the pockets of liquid are isolated. So they're not, the reaction between the solid and liquid is restricted. They're not penetrating grain boundaries. If this dihedral angle now is between 60 and 120 degrees, this ratio gamma SL over gamma SS is between 1 and the square root of 3. The liquid phase now starts to penetrate the grain boundaries. So here's an example at phi equals 90 degrees. So they're no longer isolated pockets of the slag. They're starting to penetrate the grain boundaries. If the dihedral angle is now less than 60 degrees, the ratio of gamma SS to gamma SL is greater than the square root of 3. And now the liquid phase becomes stable along the grain boundaries. And now you have isolated solid grains in a matrix of the liquid. And this would be for an angle of 45 degrees. And as this dihedral angle approaches 0, the ratio gamma SS to gamma SL is 2. And now the liquid is completely separating the grains. So this is phi equals 0. You have solid dispersed in a liquid. And this is the kind of scenario that can happen at the hot phase of a refractory, depending on how the slag wets the refractory aggregate. So that's a little bit about wetting. It's important to remember that you want to design a refractory in an application so that whatever fluid's in contact with it is non-wetting. And that's what, when we talk about the composite materials where we have a graphite matrix, essentially a graphite matrix, metals and slags are non-wetting to graphite. So that's one of the advantages of making these composite refractories. Really cuts down the corrosion rates. So we also mentioned phase diagrams at the beginning of this section. And these are equilibrium diagrams that tell you the chemical reactions that are going to take place. And we'll go over what a simple binary phase diagram looks like. And this is for dolomite, which is MgO-CaO. And what we have plotted is the temperature versus the composition. This left-hand side is 100% MgO. The right-hand side is 100% CaO. So if we're on the left-hand side, we're increasing the CaO content to 100% from 0. If we're on the right-hand side, we're increasing the MgO content from 0 to 100%. So basically, we have composition in the X direction, temperature in the Y direction. And then the phase diagram is essentially a map. It's telling you at what chemistry and what temperature, what phases are present. So if we look at this line, CAED, that's known as the liquidus curve. So any composition above this temperature of the liquidus curve is going to be a liquid. So L is liquid. So anything in this region is going to be a liquid. Obviously, you don't want to use this refractory any compositions above the liquidus temperature because you'll just have a liquid. This curve C, B, F, E, G, D is the solidus curve. So any area below this curve is completely solid. So here's a two-phase region, MgO and CaO. So you have the two different phases here. There's no liquid present. This region on this side is MgO, and SS means solid solution. So it's solid. It's primarily MgO with a little bit of CaO dissolved into the crystal structure. And then the opposite side, you have some CaO solid solution. So there's some MgO dissolved into the CaO crystal structure. They're both the same cubic crystal structure, so there's some limited solid solution. But these regions are completely solid, no liquid. MgO has a high melting point around 2800 degrees C. So the melting point is right there at point C. Point D is the melting point of CaO. It's a little lower, about 2600 degrees C. When you mix two different materials, you're going to have a eutectic melting point. So the combination is going to give a melting temperature somewhere in between, somewhat lower than either C or D, and that's point E, the eutectic. So this is the lowest melting temperature in the system, and that's at, I guess, 2370 degrees C. So I just mentioned that CBFH, this region here, is a single phase solid solution. DGI is another single phase solid solution. There are also two-phase regions. I mentioned MgO and CaO. Well, there's two different distinct phases there. And that's FGIH, that region there. There's also two other two-phase regions, and it's a solid and a liquid in both cases. So this is MgO solid plus a liquid. So that's CaEFB. And then this region is a two-phase region, CaO solid plus a liquid. That's D, G, and E. So you have a liquid, a single-phase solid region, another single-phase solid region, a two-phase solid region, and another two-phase region of a solid and liquid, and another one of a solid and a liquid. You can use something known as the lever rule. And if you pick a composition at A here, which is 40% CaO and 60% MgO, you can use the lever rule in this two-phase region to determine how much solid and liquid you have present. Any of these lines, horizontal lines connecting two of these boundaries, is known as a tie line. So B to A is a tie line. So the lever rule sounds messy, but it's real easy to use. The lever rule is the ratio of the amounts of two phases in equilibrium. The two phases are the inverse of the ratio of the lever arms connecting their respective compositions to the overall system composition. So let's just use it for an example here for composition A, which again is 40% CaO and 60% MgO. And the temperature we'll pick is just above the eutectic temperature. So we'll just be barely above 2370 degrees C. So we're at that point right there. That's the composition, and the temperature is fixed right there. So we draw a tie line from F to E. So F is actually 9% CaO, and E is 66% CaO. And we said A was 40 and 60%. So the distance from F to this composition A is 31%, and the distance from composition A to E is 26%. So 26 divided by the sum of these two, 57, is the percent solid. 31 divided by 57 is the percent liquid. So it's this lever over the tie line gives you the percent solids. So it's opposite the solid phase. 31 over 57 is opposite the liquid phase, so it's giving you the percent liquid. So it turns out at that position, you have 54.4% liquid and 45.6% solid. So you can use the lever rule and determine how much liquid and solid you have present at different compositions and temperatures in those two-phase regions. Refractories, and especially in contact with slags, there are multiple compounds present, so the chemistry is quite complex. It's not just going to be two phases like this. Even in a dolomite refractory, there's a number of other impurities. It's not pure MgO and CaO, which is what's shown in this diagram. The next step up from a binary phase diagram is a ternary phase diagram, and it has three components: Na2O in this diagram, SiO2, and Al2O3. So it's a ternary phase diagram for sodium oxide, aluminum oxide, and silicon oxide. And what you see here is you're looking down on temperature contours on the liquidous surface. And actually, each side of this phase diagram is a binary. This would be the binary between SiO2 and Al2O3. This is the binary between Al2O3 and Na2O. And this side is the binary between Na2O and SiO2. So we're looking at the liquidous surface, and there's phase fields for each different type of compound that is present, and the temperatures are given by these temperature contours. So tridymite is a form of SiO2. It's present in this region here, and you can see the compositions. This goes from 0 to 100% SiO2, and this would go from 0 to 100% Al2O3, and this would go from 0 to 100% Na2O. So you can pick a point, determine what the composition is, and then you can see from the temperature profile what the liquidous surface is, where it becomes a total liquid. So we can take a real simple case here. We'll have a refractory, which is 40% alumina and 60% silica, and we'll just say it's pure alumina and silica. That composition is right here. And we can take a slag that's 20% Na2O and 80% SiO2, and that composition is right there. And we can see by using this phase diagram how the slag is going to react chemically with the refractory. So the potential reaction products between that refractory, the alumina silica refractory, and the sodium silicate slag are located on a line connecting the refractory and the slag compositions. So at the slag refractory interface, the composition moves in the direction towards the slag composition. So as the refractory dissolves in the slag, we're moving in a direction towards the slag composition. So this is the line from the refractory to the slag composition, this red arrow. So we're moving in the direction of the red arrow, and we're going to cross various phase fields with different compounds and different melting temperatures and different liquidous contours. So the potential reaction products between the refractory and the slag are located on this line connecting the refractory and the slag. And at the slag refractory interface, the composition moves in the direction towards the slag. So the first phase field is albite, and that's the first composition in equilibrium with the refractory and the slag. Albite is Na2O, Al2O3, 6SiO2. So this compound is forming, and it has a low melting point, 1104 degrees C. So we start out with a 40% alumina, 60% silica material here, and we're in a mullite phase field. So it's a high temperature material. And all of a sudden we go into the albite phase field. So we have a compatibility triangle. 3Al2O3, 2SiO2 is mullite, SiO2 is silica, and then albite is right here. It's Na2O, Al2O3, 6SiO2, and you can't see it right here, but that melting point, 1104 degrees C, is right there at the where these two lines, yellow lines meet, 1104. Also in that phase field, you have another eutectic, a low melting eutectic between tridymite, albite, and mullite, 1050 degrees C. So you not only form a low melting material, but you have another possibility of a low melting eutectic. So all of a sudden, if the slag is reacting with the refractory, you go from a high temperature material to one about 1100 degrees C. So as long as you're above 1100 degrees C, you're going to be having a liquid phase. So I just mentioned that in this mullite silica albite triangle, you have a eutectic melting point of 1050 degrees C. And that was that point right there. So if you continue moving along that line, sodium silicate is the composition at equilibrium with the refractory and the slag. So this is the next composition, Na2O, 2SiO2, and that melting point is much lower, 874 degrees C. So now you cross into this compatibility triangle of albite, SiO2, silica, and the sodium silicate, Na2O, 2SiO2. And here's a low melting eutectic, and here's the melting point. I'm trying to find the exact melting point. There it is right there, 867. No, 874. There it is, right there. And then you have a low melting eutectic, 740. So as you move in the direction of the slag composition, you're encountering other phases that are low melting, plus a series of low melting eutectics. So I just mentioned the sodium silicate albite compatibility triangle has a eutectic point of 740 degrees C. So you can use phase diagrams. You have binary phase diagrams, you have ternary phase diagrams. You can use them to predict what reactions might happen between a particular refractory and a liquid, a slag or fluid of some sort. But a binary only has two compositions and a ternary has three compositions. So slags, refractories are much more complex than that. So they're only valuable as a first approximation. So refractories and slags contain other compounds and impurities, and those compounds and impurities in that combination usually lower the melting point substantially more than you might see in a binary or ternary phase diagram. So the best way to do this, if you want to look at compatibility between a particular slag composition and a refractory composition, you want to do a thermodynamic calculation. Those phase diagrams are determined in two ways. You can take a particular composition, hold it at a particular temperature for a long time until you reach equilibrium, quench it, X-ray it, and see what's there. And you can do that for a lot of compositions, perhaps 100 compositions, and form a phase diagram. Or if you have thermodynamic data for all the possible compounds that can form, you can do a thermodynamic calculation. So it's a complex calculation, and there are computer programs that you can buy where people have tabulated all the possible thermodynamic data for all the possible compounds. And some of these computer programs are listed here. One's called ThermoCalc, one's called FactSage. So the best way, if you're trying to determine compatibility between slags, glasses, metals, and a particular refractory composition, is to use these types of programs. They're fairly expensive. I think they run about $30,000 for the first year, and I think there's about a $5,000 upgrade each year after that. So if you're doing that kind of application where you need to know how the slags or glasses are going to react with your refractory, it's worth it to get this kind of program. So it's a good way to predict what's going to happen. So there's various static and dynamic tests that are available to measure corrosion. There's three static tests here on these three diagrams, A, B, and C, and there's three dynamic tests here, D, E, and F. The static test A, this is a Cecil drop experiment. This is what I showed with the wetting. We had this configuration. You can put a droplet of the slag on top of the refractory. So the solid dark gray is the ceramic refractory and the light gray is the liquid. You can actually see how it reacts. So you can measure this contact angle. So that's a static test. In a static test, it's not dynamic. You're not moving the sample, so there's no slag velocity, and you're not renewing the slag composition. So as the refractory dissolves in the slag is changing. This is a cup test. This is a pretty common test. You put some slag inside of a refractory cup. You heat it up. This is at temperature also. All of these are at temperature. So you heat it up till the slag is fluid. And then you cool it back down and you look at the degree of reaction between at the slag refractory interface. You can measure a cut line if some of the refractory dissolved. You can measure the penetration if the slag penetrated and dissolved or diffused into the refractory. And if you want to study it in more detail, you can cut a polished section out and look at it under a microscope and see what exactly is reacting. The other possibility is putting the refractory in the slag. So this might be a platinum crucible. The slag will not wet platinum crucible, so there's no reaction between the platinum and the slag. It's inert. It's an inert crucible. So you melt the slag in a platinum crucible and you drop in a piece of the refractory. You let it corrode, and then you pour the slag off and examine the refractory to see how much the slag penetrated, to see how much refractory is actually left. So those are static tests. There's no movement of slag over the refractory, and the slag composition is going to be altered as the refractory dissolves in it. It's going to become more viscous and less reactive. There's three dynamic tests. The first one used to be an ASTM test, but it was made obsolete. It's just a simple drip test. Slag is dripped onto an inclined surface, and it falls down that surface and it erodes the surface. So you're moving the slag over the surface and you're continually adding new slag, so you're not altering the composition of the slag. This is a finger test. It's not an ASTM test, but you're just taking a refractory bar and rotating it in a large volume of the slag. So the volume of the slag is much bigger than the refractory. So you're not altering the slag chemistry that much, and you're rotating the sample so that now you have slag moving over the sample. And this one is an ASTM test. It's a rotary slag furnace. So it's a cylinder lined with the refractory. It's rotating. There's a burner on one end, and you're dropping in slag pellets, and the slag runs from the high end to the low end and coats the refractory and reacts. So we'll describe this one in a few minutes. So static versus dynamic test. The static test, the corrosive fluid is not renewed during the test, so its composition changes as the refractory is dissolved in it. In a dynamic test, you're attempting to duplicate a real situation. You're replenishing the slag, and now the slag is moving over the refractory. So you have a flow rate past the refractory. So there's a few tests here that I picked to go over. I mentioned that porosity is real important. The higher the porosity, the more slag penetration and reaction in a refractory. So ASTM C830 is a way of measuring the porosity. Measures quite a few other things, but it measures the open porosity, which is the apparent porosity. So the apparent porosity is the volume of open pores divided by the bulk volume. So you have a volume of solid material, you have a volume of open pores, and you have a volume of closed pores. Those three make up the bulk volume. You can measure liquid absorption, how much liquid is absorbed into the open or apparent porosity. So it's the weight of liquid absorbed divided by the weight of the sample. You can calculate an apparent specific gravity. It's the weight of the sample divided by the impervious volume. So it's the volume of the solid material and the volume of the closed pores. It's apparent because you're neglecting the open porosity. And you can measure bulk density, which is the weight divided by the bulk volume. And again, the bulk volume is the volume of the solid material plus the volume of the open pores plus the volume of the closed pores. The liquids that you use in this test can be water or kerosene. Water, in some cases, can react with the refractory. It reacts with a refractory that has lime in it, hydrates the lime. So in that case, you would use a kerosene instead of water, so you won't hydrate the refractory material. So this test is used in evaluating and comparing product quality. It's part of the selection process for using refractory products. It's a great quality control test. It's also used in research and development. You can use it to evaluate for compliance specifications to see or evaluate if the material is meeting specs, and you can use it for design purposes. The sample, you start out with a 9-inch straight and you cut it in quarters, so you end up with a quarter brick. And when you do that, you'll have 4 original faces and 2 cut faces. Or you can use a refractory shape. You can cut it, but you need to have about 25 to 30 cubic inches, which is about the size of a quarter brick. And you'll end up with some cut and original faces when you have a shape that's different than a brick. Here's a quarter brick sample. It's 4.5 inches long and about 2.5 and 2 1/4 inches in cross section. To run this test, you measure the dry weight and you dry it out above the boiling point of water. Get a dry weight. Remove any physically held water. You place the samples in a vacuum chamber. You pump it down to a certain amount of vacuum, 1.9 inches of mercury. You hold that for a while, about 30 minutes. Then you allow the liquid to enter the chamber. It fills the pores. And then you also pressurize the chamber at 40 psi for an additional hour to make sure all the open pores are penetrated by the liquid. Then you measure the suspended weight. You simply hang the sample from a balance in some type of wire loop into a container of the, whatever liquid you're using. So it's suspended. And then you measure the saturated weight, and you have to blot off the extra liquid on the surface. And then you measure the saturated weight, which is the weight plus the liquid in the open pores. So there's just a series of equations for calculating these different values. The bulk volume is W minus S. So V is the bulk volume, W is the saturated weight, S is the suspended weight. The open pore volume, V0 is the saturated weight minus the dry weight. All of these cases, you have to multiply by the density of whatever liquid you're using. Actually, you're dividing by the density of the liquid you're using. And the impervious pore volume, the closed pores, VI impervious is the dry weight minus the suspended weight. The density of water in this case is taken as 1, so you don't really divide by anything. If you're using water for kerosene, it's different. So the apparent porosity, the open pores, is what you're looking for when you want to consider corrosion. The apparent porosity equals the saturated weight minus the dry weight divided by the saturated weight minus suspended weight. And to get percent, you multiply by 100. The amount of liquid absorbed into the open pores is the saturated weight minus the dry weight divided by the dry weight times 100. And then the apparent specific gravity, it's apparent because it's not including the open pores. T, the apparent specific gravity equals the dry weight divided by the dry weight minus the suspended weight. And then finally, the bulk density, B equals the dry weight divided by the saturated weight minus the suspended weight. And now these are times the density of the liquid. And again, because water is just 1. So you make all those different weight measurements. So you have a dry weight, a suspended weight, and a saturated weight. And in this particular report, it looks like kerosene was used as a liquid. So the specific gravity of kerosene is 0.8. Water is 1. So you have to account for the difference between water and kerosene. So you get an apparent porosity, a liquid absorption, a specific gravity, that's an apparent specific gravity, and a bulk density. So these are obviously insulating refractory materials. You can see that the open porosity is about 68%. So it looks to me like it's an insulating firebrick, high porosity, high liquid absorption, and low density. So that's the ASTM C830 test for determining the open porosity. I picked this other test, C577. It's a measure of permeability. So this gives you an idea of how the open pores are connected and how permeable the refractory is. So obviously for corrosion resistance, you want a material that has low permeability. So C577 measures the permeability of refractory materials at room temperature. You measure the rate of flow of air or nitrogen through the refractory material. So you're using dry air or dry nitrogen. And also, something important to remember, if there's a texture in the refractory, depending on how it's made, the permeability can vary in different directions as a function of direction in the refractory. So here's the general relationship for permeability. K equals permeability in centidarcies. So K equals M, the gas viscosity, whatever gas you're using, and that's in centipores. Q is the flow rate of that gas in cubic centimeters per second. L is the length of the sample. A is the area of the sample. That's the length is in centimeters and the area is in square centimeters. And the pressure drop across the sample is delta P in atmospheres. So centidarcies CD has this great definition. It's the flow of 0.01 cubic centimeters per second of a fluid of 1 centipoise viscosity through a 1 centimeter cube under a pressure difference of 1 atmosphere. That's difficult for me to visualize, but that's what a Sanadarcy is. So this test is useful in research and development for establishing relative permeability of products, perhaps within a comparable class of similar composition refractories. It may also be useful to identify acceptable products for designing and lining to establish permeability criteria for acceptance of a refractory for an application. So you really need to know if this is a permeable refractory or not for an application where corrosion is important. The sample size is usually a 2-inch cube. If you cut a 2-inch cube, you can have 3 original surfaces. This is an original surface. This is a cut surface. Other sample configurations could be a 2-inch tall, 2-inch diameter cylinder. And we've used all different shapes and sizes depending on how much material is available. So for the equipment, you have a rubber gasket that you seal a sample in, and you pressurize that gasket to get good contact between the sides of the sample and the gasket. You have to have a regulator to control the gas pressure. You need flow meters to measure the glass flow. And we're usually going from 0 to 9,000 cc's per minute. You need a gas, the permeating medium, and it's usually dry air or dry nitrogen. And you need a manometer of some type. The old-fashioned way is using a water or a mercury manometer, but you can also use a digital manometer, and that just measures the pressure difference across the sample. So here's a diagram of the apparatus. Your sample is sitting in here, and A is this gasket holder. So it's this metal shell, it's a cylinder, and it clamps this piece of rubber or plastic. So this is a cylinder with a 2-inch square hole in it where you fit the sample. So the sample is sitting in here. This is the rubber gasket. Each one of these fits over this. This one would fit over the top. This one would fit over the bottom. You apply a pressure to these, it squeezes the gasket and makes a tight seal between the gasket and the refractory sample. So that's sitting in here, and this is just a means. E is some type of hydraulic or screw-driven press to compress these metal plates into this gasket to make the seal. So there's your sample. So A is the gasket holder. B are drying tubes. If you're not sure, you purchase dry air or dry nitrogen. C is the manometer to measure the pressure difference across the sample. D is C is a digital manometer, and this is another way of doing it with a flow meter assembly. The flow meter assembly is actually controlling how much gas is flowing through the sample. I mentioned that E was the hydraulic jack or press, F is a valve, and G is a pressure relief valve. So you're flowing air or nitrogen through the sample, and you're controlling that with a flow meter assembly, and you're measuring the pressure drop with the manometer. So to run this test, you place the sample in the rubber gasket, seal a sample in the gasket, pass air and nitrogen through the sample, and the test has you do this at different pressure drops. So 240, 140, or 70 millimeters of mercury. using a mercury manometer or the digital manometer. So at these different pressure drops, you measure the rate of air or nitrogen flow on the low pressure side of the sample. So if you have a high rate of flow, if the material is permeable, if it's exceeding the capability of the equipment, 9,000 cc's per minute, you can then use pressure drops of water instead of mercury. So you pass air and nitrogen through the sample at pressure drops across the sample of 240, 140, or 70 millimeters of water instead of mercury. So they're much lower pressures. And then you measure the rate of flow of air and nitrogen on the low pressure side of the sample. And here are the two equations for calculating permeability. K equals this constant 0.451 times F is the flow rate in cc's per minute. dPm is the pressure drop across the sample in centimeters of mercury, and that's times 1 plus the same pressure drop divided by 152. And if you're using the water manometer, K equals 6.19 times the flow rate times dPW, which is the pressure drop across the sample in centimeters of water. And we're assuming the viscosity of air is 182.7 micropoise. If you're using nitrogen instead of air, you have to multiply by 0.95 because it's a different density gas. So you take each one of those equations and multiply it by this correction factor. And the final report looks something like this. This was a castable refractory. And if it doesn't say any other thing other than the size, it's a 2-inch cube, and it was tested in two orientations, perpendicular to the cast face and parallel to the cast face. So the answers are quite different depending if there's an original surface, which is a cast surface or not. So these are the 3 measurements in centimeters of water, the 3 measurements in centimeters of mercury. NA means you didn't get any flow in that direction, so you had to increase the pressure to get flow. So A is perpendicular to the cast face. So you had a flow of 1.23 centidarcies, then parallel to the cast face is 0.48. So this number is the average of however many measurements you're able to take over that region from 0 to 9,000 where you can measure the flow. So that's what a permeability test looks like. There's 2 corrosion tests I think I listed here. ASTM-C 621 is an isothermal test, constant temperature. It's a static test. Nothing's moving. You're just hanging a refractory bar in a crucible of glass. This is mostly used for corrosion of refractories for glass tank applications, but you can use it for any type of application. It's static. You're not changing the glass composition. You're not moving the sample or the glass, and it's isothermal at a constant temperature. You can use this for quality control, research and development, developing new refractories, and comparing products for an application. So glass tank refractories, while they operate in a dynamic environment, the glass is moving over the refractory and the glass composition is constantly renewed. So this static test may not directly predict what happens in the actual service or predict the service life. In the actual service, you have thermal gradients. Your refractory is not at the same temperature. You have a cold to hot face gradient. It doesn't take into account thermal conductivity, which in effect affects the gradient. doesn't account for the lining thickness, and it doesn't count for the action of moving molten glasses over the refractory. But it's a relatively easy test to run, and it gives you decent results, decent information. So the glass can be, the refractory sample that you use in this glass corrosion test can be a prism, and they have exact dimensions here, 0.39 inches by 0.39 inches in cross section, 2 inches long, or it can be a cylinder, 1/2 inch in diameter by 2 inches long. And the test is calling for 2 control samples and 2 unknowns. So usually you have a known material that you use as your control. And if you want to evaluate unknown materials to see if you can come up with a better material for your application, it says, well, you should test 2 controls and 2 unknowns for the best comparison. So you need a furnace with a small thermal gradient. These are small samples and small crucibles, so you don't want a gradient in your furnace. You need a temperature controller that can maintain the temperature of the furnace fairly accurately. The crucibles that are used are platinum. Again, the glass doesn't wet the platinum, so it doesn't react. So the crucible does not react with the glass and become part of the test. And you need a microscope to measure the amount of corrosion that takes place. So this is what the setup looks like. Here's your sample. It's 2 inches long. If it's a cylinder, it's a 1/2 inch diameter. Here's your platinum crucible, and this is your glass. And it specifies what all these distances are, because they all affect the result. How far the bottom of the sample is to the bottom of the crucible, the bottom of the sample to the glass line, the total amount of glass that's in the crucible, the size of the crucible. And you hang your sample with a refractory top with the hole in it. This one is zircon. You don't particularly have to use that, but you need a refractory top. And you cement the sample in so it doesn't move. So you have this fairly exact setup. So you heat the mounted sample, the sample that's mounted in the top, and the crucible that's filled with glass. You heat these two separately. In the furnace, you bring it up to test temperature. And how you start the test is you take the mounted sample and place it in the crucible. And you hold it for some time period. And at the end of the test, you go in the furnace, you remove the sample from the crucible and allow the glass to drain off of the sample. So what you end up with is a sample that has a glass cut line that usually looks like this. This is the glass cut line. This would be the bottom of the sample. So this is where the glass level was at the highest level of the glass. This sample is cut in half, so you can make these two measurements. G1 and G2 are the measurements at the glass line, how much refractory is left, the thickness. And then once you have this established, this glass cut line, you go 1/2 the distance from the glass cut line to the base, and you take a measurement H2 and H1 and take that thickness. So the glass line corrosion, GC, equals G, which is the width or diameter at the glass line before the test, and you're minus 1/2 G1 plus G2 for an average cut. So G1 plus G2 is the width or diameter of the glass at the glass line after the test, and you divide that by 2 because you're using 2 of these here. Half down corrosion, HC is the half down corrosion thickness. H is the initial width or diameter at the half down position before the test. Then H1 and H2 are the two measurements I showed. the thickness of the sample at the half down position. So you can calculate GC and HC. And this is what a sample looks like after testing. This is a 2-inch long sample. You can see the glass cut. So that's where the glass line was. And there's still some residual sample of glass on the end of the bar. So your measurement is here at the glass cut and then halfway down over here. This part was not in the glass, it's above the glass line. So you cut it carefully with a diamond saw, and you put it under a microscope and you look at it. And this line, the faint yellow line, is the cut at the glass line. So that's the thickness of the refractory that is left. So that gives you G, or one of the G's. You have 2 halves. This particular dimension is, on this one was 6.77 millimeters. And then you take the measurement at halfway down from the glass line to the bottom of the sample. And in this case, it was 9.89 millimeters. And that's your value H. And you can see the line on here. You look under a microscope, but you can see there's a little bit of glass on the surface yet. So you measure it from the actual refractory, ignoring the glass that's still on the surface. And a report would look like this. You have the initial width of the sample. It should be the same from top to bottom. It's a machine sample. You have your 2 values for G, the width at the glass line. Your 2 values for H, the width halfway down. Your glass line corrosion, and then your half down corrosion. So the corrosion on, let's say, sample number 1 was 0.57 millimeters. That's how much of the width was lost. Under the glass line, you only lost 0.04 millimeters. This test was run at 1500 C for about 2 days or 48 hours. The other test that's run a lot on refractory materials is a rotary slag test. So it describes a procedure for comparing the corrosion behavior of different refractories in contact with the molten slag. This time it's in a rotary furnace. It's a dynamic test. So the furnace is rotating, the slag is moving over the refractory surface, and you're replenishing the slag throughout the experiment. So it's a dynamic test, simulates real conditions better than a static test. And in this test, you always have or you want to always have a reference material for comparison. So simply you have a refractory that's in contact with a molten slag in a rotary furnace. You have a thermal gradient in the wall of the furnace that's determined by the type of the sample you put in the furnace. And that's why you want to use a control sample, because it's not always the same thermal gradient. Slag is constantly renewed, so you're always putting new slag in the furnace, and it's flowing over the refractory. The furnace is tilted, so it flows from the high end to the low end, and then it's simultaneously rotated to increase the amount of corrosion. This can be used for product development. It can be used to select a particular refractory for a particular application where you have a known slag composition. So there's 6 samples in this test. Each is 9 inches long. So you basically start out with a 9-inch straight brick, and you cut it so it has a cross section that looks like this. So this is your 4.5-inch width of a 9-inch straight, which would have been a rectangle. And this one is 4.5 by 3 inches. So that would have been a cross section. And you cut off the corners like this. This is an original surface. And you have 6 of those, and perpendicular to this slide would be the 9-inch direction. And then you put the samples in this, a cylinder, a metal shell, and it forms a ring that looks something like this. So a cross section of the furnace is shown here. This rectangle is basically the metal shell. There's an opening on each end. This one has an insulating material, but you don't have to use that. And actually the ASTM test doesn't really call for that. Then your sample is sitting here and here. It forms the ring inside the cylinder. You have end plugs of a different composition that's compatible with these materials. So this is the setup. This is sitting on a roller system of some type with a variable motor. You can control the speed of rotation. And you're running, this test was run at 3 revolutions per minute. So the furnace is rotating. On the low side, because it is tilted, this is the low side, this is the high side. It's not a very steep tilt. You have some type of gas burner. It could be oxygen acetylene, oxygen propane, but it's a high temperature flame and it heats this up. And you measure the temperature at the refractory slag interface with an optical pyrometer. So that's the hot end, the low end of the furnace. At the high end, you're feeding in the slag in form of a pellet every certain time interval to keep the slag flowing, and it flows out this end. So that's what the setup looks like. The slag can be synthetic, or it can be used from an operation. If you want to test the refractory for a particular operation, it's probably best to get a used slag sample with all the impurities present in it. So you grind the sample that you're using to make the slag to minus a 30 sieve, which is about 600 microns. You take that powder and you press it or extrude it into some type of pellet, about a 1-inch in diameter pellet. So those are the pellets you drop in the cold end of the furnace to form the slag. The furnace is tilted at 3 degrees. It's not that steep. It's rotated at 2.5 to 3 revolutions per minute. The slag is charged into the upper end of the furnace. The molten slag then flows through the furnace over the refractories and exits at the lower end, right in front of the burner. The temperature is measured by an optical pyrometer. And because you have a rotating furnace and you have slag that's moving, you don't get a really good measure of the test temperatures, but they're saying we'll measure it within plus or minus 10 degrees, which is probably about the best you can do. And after the test, you cut the samples perpendicular to and at the center of the slag face. So this is a refractory sample. This is the 9-inch direction. This is what it looks like after the slag test. So here's the residual slag that's on the surface. And you can see there's a cut. This used to be a horizontal surface here. There's a cut, and there's some slag penetration. And if you cross-section that sample, it looks something like this. This looks like a fire clay, or like a Super Duty fire clay refractory. And this is the cut. This used to be a horizontal line parallel to this line. So there's a cut. So you can measure the thickness of the sample before you run it, and then you measure this after. You can get the amount of cut that takes place as one measure of what happens during the test. You can measure how much slag has penetrated into the refractory, and you can see there's some slag penetration by the discoloration. And if you want to really understand what's going on, you can cut a little cube out of this, make a polar section, and do a microscopic analysis, probably with an SEM. So you can see what's being attacked, how the chemistry is changing. So you can see what's really going on by doing an SEM, scanning electron microscope study of exactly what's going on. And we get a lot of used refractories that have been attacked by some type of slag, and we do the SEM analysis to figure out what's going on and what's attacking the slag. And then we try to use the phase diagrams to predict why that occurred. So the test report looks something like this. The test temperature here was 1650 degrees C. The test was run for 5 hours, and they were feeding in 2 pounds of slag per hour. Five samples were measured. I don't know why the control sample wasn't reported here, but they measured the depth of slag cut, 0.307. So there was a slag cut. This distance here was 0.3 inches approximately. I guess the average was 0.368. And then they measured the slag penetration, and that's that darkened area here, which is about 0.1 or maybe 0.2 inches. And these are two separate runs. You know, I just made a mistake. I cut off the rest of this data. There weren't 5 samples. There were actually 6 samples. I cut off the other 4 samples. I just forgot. These measurements were made at 5 different locations along the length, okay? So that's what we did here. We took 5 measurements along the length, and that's why there's 5 numbers here, and got the average. The test does not specify how to measure anything. It just says, run the test, take a picture, here's what it looks like. But that's not really good enough. So we take sections along here, cut it, measure it, and report it like that, along with the photographs. So that's what happened here. There were actually 6 samples. I cut off the other ones, so we could see what this was. Otherwise, it'd be too small to look at. So I think that's the last slide. Are there any questions on any of this that we went over today? Okay, it's almost 2:30. Tomorrow, we'll start on the different chemistries, and we'll spend some time on a silica refractory, and then on a alumina silicate refractory. So we start out with a simple silica material. We add alumina to make the alumina silica version. And each time we go over a refractory composition, which will take the next 4 days, basically, we'll describe the raw material. We'll describe the phase diagrams. What are the phase relationships? We'll describe how the material is processed, how it is made. And then we'll look at the microstructure. We'll have some SEM photographs of what the microstructures look like, so we can see the microstructure and its chemistry. And then we'll highlight some of the properties for these materials. So tomorrow will be silica and alumina silica, and then we'll just continue next week for 3 days on the refractories. And then the last day, we'll have a session on how to design a microstructure and how to design a vessel for different applications. So if there's no more questions today, we're done. If you have any questions in the future, you can always send me an email or call me anytime on the phone. Thanks for your attention today. Thank you.